Hey, what's up, guys? This is Yiming Wang, and now I will show you the three approaches to realize a function in Project. Okay, so let me first introduce the first approach. So for this approach, firstly we need to correspond the sum of the five inputs to the 3 bits binary numbers that we want. Then I find that if I want the f0 to be 1, the sum should be 1, 3, and 5, right? 1, 3, and 5. And the same as f1 and f2. And then I draw this kind of sum table for me to quickly write down the ones or zeros on the K-map here. So let's first take a look at f2. So when f2 is 1, the sum should be 4 and 5, right? So let's take a look at the sum table, the 4 and 5 here, so we can write down the ones easily. Ones, here are the ones, right? They are 4s and 5s, and the same way as f1 and f2. So we can write down this expression here. Now let's take a look at the results for the compile. So it's totally use 15 logic elements. So let's download the code to the board. Start. Okay. Five. Okay, I put down. Let's do this again. Then we come to the second approach. Okay, let's take a look at the code. And here we go. We download it to the digit 0 board. Start. Looks great, huh? Okay, I can play it for the whole day. So the first step for this approach is to add these two numbers, x0 and x1 together, and we have a 2 bits binary number, a1, a2. It's one number, and we add these two numbers together. We have another 2 bits binary number, b1 and b0, and then we come to the second step to add these two numbers together. And the way was already taught in the problem 2.89. And here is the truth table. Here is the K-map for that. Because it outputs a 3 bits number, so we need to draw 3 K-map for this. Here is the K-map for S0. It looks exactly the same as the problem 2.89, so it's great. And I've tried the SOP form and the POS form for every K-map. And here is the K-map for S1. And here is the K-map for S2. Yeah. And the total cost shows that SOP form wins, right? Okay. Well, and I've already used the don't care terms to save some steps. Then we come to approach 3. And in this approach, we just take the advantage of the addition function in the Verilog code. And here is a way to realize a function with that. And we just need to find when we want the the output to be 1 or to be 0. For example, for F0. So here is the ones, right? And we can take a look at the sum. The sum is 1, 3, and 5. So we can use the if condition and output the F0. So if the sum is 1 or 3 or 5, I want the output of F0 to be 1, and else F0 is 0. And the same as F1 and F2. And here are the results for the compile. It uses 11 logic elements. And then let's take a look at that, how it runs well on this board. Programmer start. Okay. And here is the RTL viewer of the logic gates for all three approaches. Here is the logic gates for approach 1, approach 2, and approach 3. And I've counted on this graph, and the first approach uses 63 logic gates. And the total cost for the second approach is just 50. Personally speaking, I like the third approach best because it's the most user-friendly to the programmers. We just need to know what the input conditions are and to decide the output for that. It's just like programming using the C language. However, I have to say that the second approach is the best because it uses the least number of logic elements. Maybe it's because we are trying to optimize the computing progress in this approach. And when the computing progress is optimized, the circuit itself is optimized.